Howdy. Let's write the formulas for angular momentum that we will need today to solve problems. First of all, the definition of angular momentum, L. We call angular momentum L, it's a vector, and by definition, it is R cross P, where P is linear momentum mv, and R is from the point of origin, from the pivot, to the point where the particle is. For example, I have a rod that is pivoted right here about this point O, and this is view from above. And this rod has length little l. And I shoot a bullet right at the end with velocity v naught. So the linear momentum of this bullet is mv naught. And r is from O to this point. This is r. And as particle is moving, r will be changing. Now, what is cross product? Cross product, L, is magnitude of r, magnitude of p, times sine of angle between them. This is cross product, which means that similar to what we did when we talked about torque, also cross product. This is a vector on the left, so I have to put a sign for the vector. I will put right hand rule here. So to find the direction of angular momentum, to find the direction of cross product, we use right hand rule. Now, if I have two vectors and I'm looking for cross product between them, we remember that we are looking for perpendicular components. We are looking for components of r and p that are perpendicular to each other. So this is my v or p. Which component of r is perpendicular to v? R has two components, horizontal and vertical. Obviously, vertical component is parallel to v. So what I'm looking for this horizontal component of r. And horizontal component of r is length of this rod. So what will be angular momentum of this bullet with respect to point O? L is a vector, and it will be mv naught L, since component of r that we are looking for is L. And now I need to find the direction. To find the direction, always bring P and R to the same point. P is up, R is this way. This is P, this is R. Now I find cross product. You need to use your right hand. I'm using my left hand because you see my mirrored image. So now you put your fingers along R. You cannot mix the order because you will get wrong direction of angular momentum then. R always goes first. You put your fingers, first of all, narrow down your choices before you start playing with your fingers. Because cross product is always perpendicular to the plane of original two vectors. So which choices do you have? Either into the board or out of the board. And now life is much easier because you put your fingers along R, you bend them towards P, and then your thumb shows you the direction of angular momentum. In this case, it is out of the board. This is the direction of angular momentum, so I denote it as this, which means out, or I just write in words out of the board. Or you introduce coordinate system. For example, this is my origin, this is x, this is y, x, y, z, follow right hand rule. So z will be out with this choice of x and y, and I can write in other words that it is this, or I can express it as iz. In terms of unit vectors, it will be along positive direction of z. Okay, next we need to know what is angular momentum in polar coordinates. We introduced polar coordinates, so this is x, y coordinate system. This is trajectory of the particle. This is r and theta, polar coordinates. We introduced unit vectors that are IR and I theta, perpendicular to IR, two unit vectors. And I want to write angular momentum in polar coordinates. So L is R cross P. R in polar coordinates is RIR, unit vector along R. P in polar coordinates is M, and velocity has two components, VR, IR, plus V theta, I theta. VR is dr dt, IR, and V theta is R omega, I theta. Now I bring P back, R and P back here. Remember that we are looking for perpendicular components. So IR cross IR will give me 0. All I'm interested in is IR cross I theta or I theta cross IR. So R is RIR. Cross product P, which is M, and then dr dt IR plus R omega I theta. IR cross IR, 0. IR cross I theta is not 0. Let's collect scalars first. M, R, and then R omega, which is V theta. And then IR cross I theta, IR cross I theta, I will call it IZ. Or we can write right-hand rule, but we have to put something for the direction. And I have M R squared omega IZ. I skipped one formula, but it is right here, M R V theta. So let me just write it here also. Another formula is M R V theta IZ. Because when I find cross product, I will have IR I theta. This is V theta. So MR V theta, MR squared omega IZ. Great. So now we have all these formulas for angular momentum, which one to use. We will be solving problems and we will figure out which one to use. So if you're provided with linear velocity, like in this case, you go R cross P. If there is linear velocity but tangential component is given, then it is MR V theta. If you have omega given, then MR squared omega. And we need to introduce one more definition. We need to introduce moment of inertia. Moment of inertia of the object I has to be introduced with respect to some axis of rotation. It is M. This is a point object. So point with mass M. M R squared. So for example, you have a rod and this rod is massless. And this rod can rotate about this axis of rotation. And I have M1 sitting right here, which is distance R1 from the axis of rotation. Okay? What is moment of inertia of this point block M1, point mass? Moment of inertia is M1, distance from the axis of rotation squared. If I add another block here, M2, and this M2 is distance, let's say R2 from the axis of rotation, then the total for this situation for two of them, the moment of inertia of the system, I, will be M1 R1 squared plus M2 R2 squared. But what will we do if the rod is not massless? Now the rod has mass. If the rod has mass, we can calculate moment of inertia of this rod, and you have problems like this in your homework. For example, what will be the moment of inertia of the rod with mass m rotating about the axis through its center? You have this problem in the homework, and the answer is m, and then length of the rod, let's call it again L, m, L squared over 12. Or you have a disk. This is view from above. What is moment of inertia of the disk? Now you have to integrate. You cannot just write it for a point mass. You take a ring and then you integrate over all these rings that make this disk. And moment of inertia of the disk about the axis through the center is m radius squared over 2. I'm writing where you cannot see. Let me just move it here. So it is, for this one, it will be m of the disk r squared over 2. Bottom line, so when you have several point particles, what you do, you just have to add all of them. It will be mi ri squared. I is from 1 to number of particles, and when you have extended mass object that is not a point mass, then you have to integrate and to find moment of inertia of such an object. Okay, but look at this, at our formula. Let's continue our formulas for L. What is mr squared? It is moment of inertia. So I add it here. It is I omega, and this will work also for the disk, for extended object, for the rod, for everything. I omega. I need to add right hand rule. And now we have all formulas that we need to find angular momentum. Now, we know that tau external from the lecture. Let me think for a second where to write. I'll probably do it right here. From the lecture, we know that tau external torque is equal to dl total for the system, dt. Change in total momentum of the angular momentum of the system is equal to external torque. What happens now if tau external is 0? If tau external is 0, then derivative dl total dt is 0, and I have conservation of angular momentum. L initial is equal to L final. Please remember that this is a vector equation. So if torque, external torque, in some direction is 0, then angular momentum in that direction will be conserved. So for example, I have rotation in z direction. So if there is no torque in z direction, then I have z component of angular momentum conserved. And we will use it a lot to solve our problems. L initial is equal to L final if external torque is 0. And the last formula that we will need today is for rigid bodies. So now what we will consider rods or platforms that don't change their sizes, rigid bodies. So for example, I will, let's just write it, rigid bodies. You can see it here, great. So R is constant. R is constant. For example, disk. We are talking about a disk. And now let's write what we have. Tau external. Tau external is dl total. dl total dt. Now L total I will write as I omega. So it is d dt I omega. Now I take this derivative. I take the derivative. I is mr squared. So what is derivative of mr squared? Where is my I? I is mr squared. So I use product rule. It is di dt omega plus I d omega dt. Di dt is 0 because I is constant for rigid objects. So this is 0. It is ml squared over 12, mr squared over 2, whatever object you consider. So the first guy is 0 and the second guy is I. And d omega dt is angular acceleration alpha. So, and I forgot the direction. It follows, the direction follows right-hand rule. Now we have the last formula that we will use to solve problems. Tau external is equal to I alpha right-hand rule. We are ready to solve problems.